Okay, welcome folks. So I'm going to try something new with this. I didn't have a ton of time in class to go over as many problems from the worksheet as I wanted. So I'm going to go over question number 13 on your worksheet. It's the middle of the second page of your coefficient of friction worksheet in this video. So if you need help on that, this video will walk you through it, because that problem is a little tricky. Okay, so here's your worksheet. Coefficient of friction. It says WKS number 1, I think. Yeah. Okay. So if we go to the worksheet, we see that it starts with a 25.6 kilogram rocket, accelerates upward, yada, yada, yada. Okay, first things first, with any of these word problems where it just starts throwing variables and values of different things at you, it really, really helps me to draw some sort of picture with the problem. Okay, before I even finish the problem. So I can see, if we start the problem, it says a 25.6 kilogram rocket accelerates upward. Okay, before I move on, I want to draw some sort of picture so that I can put my thoughts on paper while I do this. Okay, this is the worst drawn rocket known to man. There's thrust. That's a rocket. Okay. What does it say first? So once we have our rocket, let's find our center of gravity for that rocket, because we're going to end up drawing a force diagram with it of the different forces acting on this rocket. And you want to start that diagram from the center of gravity of whatever object you have. Okay. So we already know, make sure I'm in view here. We already know that the mass of this rocket, mass equals, I'm going to use both colors here, 25.6 kilograms. And remember, with any type of physics problem, all of the equations are set up to work with a mass that's in kilograms. So if your mass is not in kilograms, convert it to kilograms. Otherwise, it won't really work. Okay, now the problem continues and says it accelerates upward at an acceleration of 105 meters a second squared. So we know that acceleration equals 105 meters a second squared. Okay, and that's of this rocket. So I can put A of R, I'm just going to leave it. All right, if the friction of the air is 100 newtons, so now we have a force acting on our rocket. And that would be the force of friction, right? Because friction is always a force. And it's caused by the air resistance, which means if this rocket is going upward, any type of resistance is going to be going the opposite direction, right? Trying to slow this rocket down. So I'm going to say the F of A for air resistance is, and since it's going downward, we're going to make those negatives, right? 100 newtons. Because when we end up getting the sum force, we want to have subtracted those to get the force of the thrust, right? Okay, what is the thrust force pushing it up? So speaking of, we have these engines firing off, and it is making this rocket accelerate upward. Notice how my arrow for the thrust force is a lot longer than this, because I know the rocket is traveling upward. So the force arrows are going to be, when we add them up, are going to end up being longer going up. So we know, well, it asks us force of thrust. So F of T equals what? Oh, and I guess to be consistent, I'll do this in blue as well. Negative 100 newtons. Okay. Also, let's think about this. Let's think about this for a second. If this rocket is flying upward, and unless it specifies, we always just assume it's on our planet, Earth, right? There's something else affecting this rocket, okay? Air resistance is not the only thing. As you've probably guessed, with any object on Earth, anyway, unless it's in space, right? If you draw a force body diagram of any object, you're going to want to factor in the weight of that object. So the F of W. And seeing that this rocket is not on a flat surface, right? That force of weight, it doesn't have a normal force, right? It's in the air. So the force of weight is going to be factored into it. All right. So now let's think about this. We have to get F of T. Okay? And F of T would equal F of T, we find that we can't simply take this mass and this acceleration, because this acceleration is not, solely factored. There's other things affecting this acceleration. What affects this acceleration is the opposing forces. So the force of thrust would not simply be 105 times 25.6, even though that's what a lot of people might think. Remember, that acceleration is being affected by the stuff pulling the rocket down. So we can say that F of T is the sum force, and remember the sum force is F of T plus F of A plus F of W. It's all the forces combined. And that's why I made these forces negative, because when you add them up, it's going to be subtracted from this arrow, right? These arrows going opposite will cancel out some of this arrow going upward. Okay, so F of T would equal the sum force of this rocket minus these forces. Minus F of A and minus F of W. Or you could say minus, in parentheses, F of A plus F of W. But we can put it that way as well. Okay? Okay, so we have F of A, we have F of W. We don't know F of T. We're trying to solve for F of T. So the one thing we do need to find is our net force on this rocket. And we can do that fairly easily, because this acceleration is factoring in all of these forces. That's what makes this acceleration 105 meters a second squared. Okay? So we can say that the net force, just know that we're trying to solve for F of T. This is what we're trying to get, right? F of T is up here. But we need the net force first. And the net force is, remember, the force of anything equals mass times acceleration, right? So we can say that the sum force is 25.6 kilograms, because that's our mass of the rocket, multiplied by the acceleration, which is 105 meters a second squared. Okay, if you multiply those two together, sorry, let me pull up my calculator real quick. We got 25.6 times 105, times 105. You end up getting a net force of 2,688. And force is always in newtons, right? So now we need to get, we need to subtract the F of A and the F of W. And I said we had this, however, we don't actually have F of W yet. So let's figure out F of W real quick. Remember, F of W is some type of MA, it's the mass, times the acceleration that's affecting it. The acceleration that's affecting the weight of anything is the acceleration due to the gravity, right? So F of W would equal 25.6, because that's the mass, times gravity. And on Earth, gravity, A of G on Earth is always 9.8 meters a second squared. Or, for the sake of any problem you do in this class, you can just round that to 10. right? And actually, it's when you do a vector problems like this, you want acceleration to be a vector, so it'll be -10. All right? So multiplied by -10. So f of w, the weight of it would be negative, and we multiply that by 10. You just move the decimal over one spot. Negative 256 newtons. Okay? So we add this up. That's negative 256 newtons. All right, now the total vector force pulling this rocket downward would be these just combined, right? So if you take negative 256 and you add negative 100, you would get a net downward force of negative 356. Okay, I'm not sure what you would call that. F of y, maybe? That wouldn't be the total F of y. Anyway, so we know that we have to take F of A and F of W. I guess we could have just used them separate or have them together. So we take the net force, which is 2,688 newtons, and you subtract F of, we'll just do them separate because that's what I wrote up here. Okay, so minus, remember we gotta subtract these, but if we subtract a negative number, a double negative is a positive. So we're gonna add 100 newtons, and then we're going to subtract negative 256, which would be plus 256 newtons, and we end up getting the force of our thrust. Hopefully you can still see this down here. Yeah. So our F of t would then be, remember, because F of t is all of this, we're just plugging it in. So that's how you get your answer. 2688 plus 100 plus 256. You end up getting the force of the thrust of the engines is 3,044 newtons. Okay. And that's how you get that problem. Done.